Okay, let me see. All right. Welcome, everyone. Hello. How's it going? So, first of all, I want to thank everybody for coming today. So, we're so happy to have you here with us today at once another Deep Learning Sessions Meetup. My name is Lucas Soares. I'm one of the co-organizers of the Meetup group. And today, we're very happy to welcome José Moreira. Now, José did his master's in informatics at the University of Porto and in the area of deep learning and computer vision. He has been working at Deloitte since 2016, mainly doing work in the area of the data science and machine learning, focused in the banking and insurance area. And more recently, he has been involved in the prototype of initiatives involving deep reinforcement learning, which is why he's here with us today to share a little bit of that experience. So first of all, I want to welcome José.
Hi, hello. Thank you, Lucas.
Welcome. Thank you so much for coming. Thank you so much for joining us here today. So José is going to be talking to us a little bit today about offline reinforcement learning. So now I'll let you take it away. And at the end, we'll have a Q&A session where you'll be able to ask your questions, and we'll try to have José answer as many questions as we can. All right? So José, the floor is yours. Thank you.
Okay. Thank you, Lucas, and thanks to the organization for the invitation. So now to the session. I'll talk to you for the next few minutes about offline reinforcement learning, which is an area which we at Deloitte are actively pursuing as an interesting area for real-world applications in various areas, and especially in the fields where I usually work, which is the banking industry and the insurance industry. So starting by telling you about the main objectives for the session. So I'll start by doing a very, very brief introduction to reinforcement learning and trying to set the field for the rest of the talk, making the case for why reinforcement learning is an interesting framework for real-world applications. Then I'll switch to offline reinforcement learning, trying to explain what it is and how it differs from the reinforcement learning usual setup. I'll then go into the main challenges that arise when we try to focus on offline reinforcement learning. Then going to explain mainly two different approaches to offline reinforcement learning. Finishing by talking a little bit about some unresolved issues in offline reinforcement learning and open research topics, and then I'll try to show you a little demo of one of the approaches which I'll talk during the session, hopefully to make it more concrete what we're talking about. So starting by making the transition from supervised learning to reinforcement learning, only because supervised learning is more, I'd say, popular or more common framework for most machine learning practitioners. So the supervised learning, as most of you know, is a framework where we typically have a bunch of samples and a bunch of labels, and we have a model that we want to be able to guess the label for unseen samples. So we usually, especially if we're using deep learning models, we transform this problem into an optimization problem, and we try to fit our model to the labels. And hopefully, by giving it enough examples and using an adequate features and everything, the model will learn how to predict the labels for future samples. This is a paradigm which is basically teaching by example. We give the algorithm a bunch of examples, and we hope it will learn the distinction between the various examples in a sense. In reinforcement learning, At first sight, we might think that the framework is similar, at least seen from these diagrams. But in fact, firstly, we don't have labels anymore. We have something which is called the reward, which is somehow different. And we have this kind of interactive process where we elicit samples from the environment, and we try to come up with a policy which produces actions that are good in this environment for the particular task we're doing. So going a little bit further into the reinforcement learning framework. So we basically usually have an environment, we sense the environment, we have a state representation of this environment, we have our agent, which is trying to produce actions which are used in the environment, which in turn returns a new state and a reward. This is the basic framework. Most of the reinforcement learning literature can be described in this dichotomy between the policy improvement and the policy evaluation steps, which interact to produce a policy to interact with this environment. But basically, what I want you to understand from this slide is that there is some kind of feedback mechanism which is not present in supervised learning, and therefore this works in a relatively different way, which makes it, I claim, more interesting for real-world applications. Mainly because of, I believe, two things. The first thing is that all this framework, all this MDP framework, which was described in the previous call about deep reinforcement learning, kind of embeds this sequential nature of some problems, which is very helpful when we're dealing with the real-world problems, because most of them, or many of them at least, can be described in this sequential nature where we interact and we get a reward back. And secondly, and perhaps most importantly, we kind of can dispense with labels, and instead we'll use something which is called a reward, which is more relaxed in the sense that it doesn't have to prescribe, or it shouldn't at least prescribe correct behavior, which allows us to use these kinds of machine learning algorithms for problems where we don't, where we might not know the correct behavior, or even if we know the correct behavior, we might use it while not having to specify this correct behavior, which is useful in many tasks. I can think of things like self-driving cars. It is very difficult to label each, for example, each frame of a video and say what should exactly be the steering level of the steering wheel, but it is usually very easy to understand how well the situation looks. So this kind of represents this dichotomy between rewards and labels. And now to offline reinforcement learning. So offline reinforcement learning, I think, kind of alleviates some of the problems that reinforcement learning still has, and some of the problems that still exist in the application of reinforcement learning to real world problems. And I'll start by defining what offline reinforcement learning is. So offline reinforcement learning is a set of reinforcement learning algorithms that basically require no interaction with an environment to be trained. It goes by many names. In the literature, you'll find the ones you can see there on the right, and there are a couple more. But basically, the important part of the definition, I believe, is the part about not requiring interaction with the environment, which is very helpful if we don't have the environment to start with, or if it is too costly to build the environment or the simulation to train our agents in. And this basically implies that if we're not using the environment, we'll be learning from a fixed batch of data, which was potentially gathered previously, possibly from human interactions with a real world problem, or by using other agents or something of the sort. It is very important to notice that this is fundamentally different from things like behavioral cloning, because behavioral cloning aims to reproduce the behavior that is seen on the batch of data. And here we're trying to go a little bit further and try to improve on the behavior that we can see on the batch of data. So we're trying to train a policy that is a little bit better than the one that was used to gather this fixed batch of data. And it is also different from a paradigm which we have seen for the past, I'd say, 3 to 4 years in reinforcement learning, which is an effort to use pre-training as a way to speed conversions of RL models, making them more sample efficient. So the idea here is that in offline reinforcement learning, you don't have the environment to, after initialization, train your model. So we don't have this environment, or possibly we don't have this environment to fine-tune our model. So we are not only doing initialization of our model, we're training the model all the way without requiring an environment. So now, if we take a step back and we go back to reinforcement learning, and we take a look at least the most mainstream advancements in reinforcement learning in the past few years, you see things like the superhuman scores in the Atari games, the AlphaGo thing, the Dex3 examples from OpenAI, and a couple other things. And they all have a thing in common, which is they all, or almost all of them, rely on the existence of a cheap way to get samples and to interact with an environment or a simulator. And this is, as I told you before, sometimes this is an impediment to the use of reinforcement learning in a real problem, because sometimes we don't have this environment. So some questions come to mind, mainly, why is this the case that we are so dependent on these simulation environments? Does it have to be like that, or can we do it any other way, which would dispense with those simulation environments? And if this is an acceptable constraint, if you want to apply these algorithms to real-world problems, as many real-world problems as possible. And to answer the first question, I would say that probably the reason why we are so dependent on the simulation environments to achieve those things is because some of these models are deep learning models, and we all know that deep learning models usually need data, and a lot of data usually. So a cheap way to get this data is a prerequisite for achieving these things. And answering the second question, what the offline reinforcement learning literature has been showing is that it is not the case that this is a fixed requirement, this of having the simulation environment available for eliciting samples. And answering the third question, I'll say that, well, as I hinted before, well, simulation environments are costly to build in some situations, especially if you're talking about real-world problems and not toy games like you see in the OpenAI gym and things like that. And they sometimes require expert knowledge. And sometimes you're trying to use or train an RL agent exactly because you want to dispense with the expert knowledge being required to operate a certain environment. So this is a problem that when overcame can potentially allow for the usage of reinforcement learning in other settings. And secondly,
sometimes it is even if we had the expert to build the simulations, even if you had the resources to build the simulation, it would be impossible to do it, because there are systems for which we don't know how they function, or they function in a way that is so complicated that it is very difficult to build a reliable simulation. And the simulation has to be somehow reliable, so that we can later apply things like transfer learning to transfer what was learned on this environment to the real world. So this might even exacerbate the problem. And when this simulation environment is impossible to build for some reason, there are situations where interacting with the real world is unacceptable and can't be done. I'm thinking here of things like medical applications of reinforcement learning. You can't possibly try to deploy an untrained reinforcement learning model on a patient or to treat a patient. It is too risky to do it, so we can't possibly do it. Self-driving cars are another example. So you can't deploy an untrained model on a self-driving car, because it will, well, break probably. So those are some of the problems that perhaps could be avoided if we avoided this dependence on simulation environments altogether. Look at the various algorithms in the reinforcement learning literature. There are various classifications that are used to divide them and group them, but mainly there is a distinction which is useful here in making the transition from reinforcement learning to offline reinforcement learning, which are the offline off-policy algorithms, which, as is listed here, is basically a set of algorithms for which we have a policy interacting with an environment that doesn't have to necessarily be the same as the one which is being optimized. And an example of an algorithm of this sort is the DQN, which was also presented in the last session. So I hope you're at least vaguely familiar with it. So this is the pseudocode for the DQN paper, the original DQN paper. And among other things, one of the novelties which was introduced here was the usage of a replay buffer, or a batch of data which is used to accelerate the convergence of the QNet. And if we look closely at the algorithm, it also uses something which is called epsilon greedy exploration, which basically tells you that sometimes to fill this replay buffer, you sometimes take actions which are chosen at random. And sometimes you use the policy that is greedy with respect to the QNet, but sometimes you just take actions at random. So in fact, what happens is that the transitions that are stored in the buffer are actually not all belonging to the policy being optimized, as I told you before. So you have here a situation where you have your QNet being trained on data that at least not all of it came from the policy which is greedy with respect to the QNet. So we might think that, well, we can take this as a little step further, and probably we can get rid of this epsilon thing and just get our pre-gathered batch of data, feed it to the replay buffer, and run DQN on top of it and see if it works. So, and it requires some thinking to try to understand what could potentially go wrong in this situation. And to get into that, I propose that we analyze the consequences of going completely offline in this situation. Firstly, we are completely making exploration completely out of scope. So if we're using a batch of data which was previously gathered, we no longer have the opportunity here to explore a little bit more and try to get a better understanding of some regions of the state space which we don't have data for. So this is completely out of scope. And we're bound to have to answer a bunch of what-if questions here, because we have a batch of data, and we're trying not only to do as well as the agent which was used to gather the batch did, but we're trying to do a little bit better. So we were bound to have to do some things differently. So we're bound to have to understand what would happen if we did this and not that. That was done by the agent that gathered the data. So these are the two main consequences of going completely offline, and they bring problems with them. And basically the main problem that happens here is that, so now in the case of DQN, what we had is a batch of data which was very closely related to the data that we would see if we would use the policy which is greedy with respect to the QNet. So if we look at the distribution of states, the one in the batch and the one that we would have if we followed the QNet advice, basically they are very similar one to the other. So there probably won't be many states that we see in the batch that wouldn't be there if we use the QNet and vice versa. So, but if we are pre-filling this batch with a bunch of data coming from potentially even a non-reinforcement learning agent, it could be a human generating this data, we're bound to be training an agent which will almost certainly produce a policy which is very different from the one that was used to produce the batch of data. So we have here a problem which usually goes by the name of distributional shift or distributional mismatch, which basically tells us that, well, we assume at the start when we use these types of models in reinforcement learning, we assume that the data during test time or during production will be very similar to the data we'll see during training. So, and most reinforcement learning algorithms are built on top of models which make this assumption. And we're breaking this assumption potentially with the dire consequences here, because we are using data that is potentially totally unrelated with the data that we'll see during test. This is the case because probably the agent that will be trained on the batch of data will take diverse actions than the one that was taken, than the actions that were taken in the batch. So it will probably see states which are not in the batch at all, or some which are in the batch only a few times, and for which we don't have a lot of epistemic evidence. And this distributional shift is only exacerbated by the sequential nature of the problem, and the fact that we're also bootstrapping our estimates of the Q function, at least in some models. So this will probably propagate the error we're incurring in some states to the whole set of states, and even states for which we have evidence will come to have an estimate of their value which is unreliable. So this makes the problem only a little bit worse. So what can be done with by being aware of the problem, of this particular problem? What can we do? So the basic idea here is that what we'll do is we'll try to make pi so that the distribution of states under pi will be similar to the distribution of states under the behavioral policy. That is the policy that was used to gather the data in the first place. And there are many ways to achieve this. I'll talk about mainly two of them, and I'll say something about other methods here. So the first family of methods to tackle this problem is called policy constraint methods, and basically what they do is that they try to explicitly make pi be close to pi behavioral. By doing this, we're basically guaranteeing, in a sense, that we won't see out of distribution states, because if pi is similar to pi behavioral, it will have a visitation pattern which is, we hope, similar. So we make some assumptions here, namely that actions that are similar will produce similar results, in the sense that it will result in a similar visitation pattern. And we also assume that making the policy be close to the behavioral policy is actually a good thing. And while the first assumption here is quite, I'd say, reasonable, the second one is not as much, as I'll tell you in a brief moment. So here on the right is the pseudocode for an algorithm which belongs to this family of algorithms, which is basically a variation of DDPG or GQN, if you wish, adapted to overcome this problem of the distributional shift. We would see if we were using a batch of data which is potentially unrelated to the policy being optimized. So the basic idea here is that we split our problem into two different parts. In the first part, we'll try to train a model to do behavioral cloning. So hopefully coming up with a policy that is very, very similar to the one that was used to gather the data on the batch. And then we'll train another model, which is here called a perturbation model, which will try to slightly change the actions that are produced by the behavioral cloning agent, and so that they are a little bit better than the original actions. And by constraining this perturbation to be between a small set of values, we hope that will induce a pattern, a visitation pattern of the state, which is similar to the behavioral policy, and therefore avoid out of distribution states and the impact that it might have on our estimate of the optimal action. So, going a little bit into the details of how this is operationalized. So this uses a variation autoencoder here, and so I won't get very much into the details of this, but a variation autoencoder is basically an autoencoder that produces the parameter for a distribution which is sampled for the decoder, and then the decoder is trying to usually to reconstruct what was fed, the input that was fed to the encoder, and we sometimes condition this on some constraints. And here the decoder and the encoder are constrained on the state. So we basically feed an action to the variation autoencoder, the encoder part. We feed it the state. It produces a latent representation. This latent representation is then fed, or values sampled from this latent representation are fed to the decoder. The decoder also receives the state, and then hopefully it will produce an action which was similar to the action that it saw on the input. And then we train this on the reconstruction error, which is basically trying to minimize the difference between the reconstructed action and the action that was used as input. We then condition this also the parameters of the distribution to be somehow near to 0 mean and 1 as standard deviation for mainly two reasons. Firstly, to make it easy for us to later query the decoder, and lastly, because it acts as some kind of regularization for the whole thing. So this is how this behavioral cloning thing is trained. And now I'll go into the details of how this is used to actually produce actions. So we make the reconstruction error and the KL divergence here with the normal distribution. We sum it and we try to minimize this for training. And then when we're trying to produce actions, we basically get rid of the encoder because we don't need it. We still feed the state to the decoder. We sample from a normal distribution and we feed the values to the decoder. The decoder will hopefully come up with an action which is similar to the ones that are on the batch. So this is the behavioral cloning part. We then have the perturbation network, which is fed the state and the behavioral cloning action, and it produces an augmentation to this action. We then sum the augmentation to the action, and hopefully we can feed this to the critic, and the critic, and by backpropagating, we can then feed then adjust the weights on the perturbation network. So the remaining of the algorithm is pretty standard as a RL algorithm. So we bootstrap our estimates of the Q function. For training the perturbation network, as I told you, we use we backpropagate all the way from the critic to the perturbation network. And the rest, apart from some details, which I'll talk more in detail in the demo, this is pretty much standard RL things. So this was just to give you a brief understanding of how the VAA is used here. So if you want to look this into with the lens of actor-critic method, so you can see all this whole thing as the actor part, okay? And then you have your pretty standard critic there. So going into the second family of algorithms which are used here, they go by the name of uncertainty estimation methods. And here the idea is somehow different. So instead of trying to explicitly make pi to be close to pi behavioral, we will try to measure the uncertainty we have in our estimation of the value of a given state action pair or something similar to this, hoping that the uncertainty we measure on states that are out of distribution is bigger than the uncertainty we'll see for states for which we have epistemic evidence. So the way this is done can vary a little bit, but the most usual approach is to use, instead of using a critic or a QNet, we'll use a bunch of QNets, and we'll be conservative in a way that we update, we make updates to this critic based on the maximum and the minimum values for the value of the state action pair. So basically here in this case, what is done is that we train a bunch of QNets, and then we use a convex combination of the minimum and the maximum estimate of the value of a state to bootstrap our QNet error. And therefore, we provide the algorithm with a conservative estimate of what is the possible value of a given state. So going back, so again, going a little bit back to the assumptions part. So the assumption here is that you'll have less variance in the estimation of the value of your state if this is a distribution. This is a state which comes from a distribution of data which you already seen. If this is an out of distribution state, you implicitly expect this variance to be big, and therefore the minimum estimate and the maximum estimate will be further apart. So this is the underlying assumption here. Here in this particular paper, another subtlety is used, which is, well, when we are trying to devise the policy, we do the optimization subject to a constraint. Here, the constraint is that well, we don't want our policy to be close to be very different from the distribute, so to produce states which are very different from the states we saw during training. And we explicitly apply a constraint here, which is basically here in this case, it is using at least in one of the settings, the maximum mean discrepancy, which basically is a measure of the difference between the two distributions, which doesn't require you to estimate the density of the distributions, which is quite useful here. So, and since we are having a hard constraint here, we have a hard constraint here to be able to use the standard neural network optimizer to optimize this problem. We convert this into the dual problem, and we use the Lagrange multipliers to be able to use our standard optimizers to optimize this problem and to get basically rid of the hard constraint we have there. And as you can see there from equation 1, this constraint is nothing more than the usage of an idea which came from the previous set of methods, which is we're trying to explicitly constrain the policy. So it often happens that the methods are not purely uncertainty estimation based or purely policy constraint based, but they sometimes mix the two ideas together in a sense. So comparing the two methods, as I told you, so in the policy constraint methods, we're explicitly trying to make pi and pi behavioral be close, but this is not always a good thing, and this is the case, especially if we have, for example, a behavioral policy which is uniform in a way that it visits states. So imagine you're gathering data with an agent which it doesn't have a clear purpose, it's just gathering data. It has no clear task, or it is trying to do one task, and then you have another agent which is trying to do another task, and you merge this data together. So we have an uniform visitation pattern of your states. In this situation, you actually don't want to make pi be close to pi behavioral, because by doing so, you're actually preventing the learning process, because basically, if your policy is to be close to the behavioral policy, and the behavioral policy is uniform in this sense, it basically means that your pi policy will be approximately uniform, which most certainly won't be very good for performance reasons. So from this perspective, it is pretty much clear, I think, that uncertainty estimation methods are more, I'd say, theoretically appealing than the policy constraint methods, mainly because an uncertainty estimation method here, what we'll try to do is try to avoid avoid overestimates of states that are out of distribution. And since our behavioral policy is uniform, we'll have data from all the states, so we won't have out of distribution states. So it would, at least in these settings, theoretically, it would be better to use an uncertainty estimation method over a policy constraint method. In practice, it happens that the uncertainty estimation methods are somehow hard to parameterize, I'd say, and it is very difficult to achieve a desirable performance if we're using purely uncertainty estimation methods, even when the distribution, the behavior policy is similar to a uniform policy. And therefore, you end up usually using a mix of the two approaches. So this is just an illustration of what I was trying to tell you before, which is, well, if you have a uniform visitation pattern of the states, you don't have out of distribution states, so you don't have to restrict pi to be close to pi behavior. Now,
talking a little bit about other approaches that can be used to tackle these offline reinforcement learning problems. So there are some literature about applying importance sampling or a variation of importance sampling to policy gradient methods that were initially designed for off-policy algorithms, but can be extrapolated to offline reinforcement learning settings and possibly achieve good results. But the main problem with this kind of approaches is that importance sampling often suffers from high variance, and so much so in settings where we have this sequentiality and we have to kind of multiply several multipliers which are trying to adjust the importance of a particular sample when we're trying to compute the gradients on the policy, and this is a problem when applying this method. So they are generally not as successful, at least till now, as the other methods I showed you before. This is just an illustration of what would happen. I told you about these multipliers having to be multiplied ones with the others along the trajectory, which might lead to even higher variance. So, and then there are other approaches which are not especially devised for offline reinforcement learning. Namely, there is some research that points that distributional DQN and the methods that try to not only estimate the average return and the average value of a state and try to model the whole distribution, they kind of seem to work well with the offline reinforcement learning setting. So this is it is possible to apply these methods to offline reinforcement learning with relative success. And now going to the last thing I wanted to talk to you about, and getting a little bit into the important issues that are still remaining in offline reinforcement learning, and some open research questions and problems that are still very much untouched for the most part. There is a clear problem here that is not yet figured out, which is, well, we know that sample acquisition has a big impact on the performance of an offline, of a downstream offline reinforcement learning agent. Namely, as I told you before, if you have an agent which is trained, if you have an agent which is not an RL-based agent, for example, a human, which is used to gather the data, and then you use this data to try to train an offline reinforcement learning algorithm, which is typically based on the Markovian assumption that all the information that is needed to obtain the optimal action is embedded in the state representation. And if the agent that was used to gather the data doesn't follow this property,
maybe this property doesn't hold, and it might be difficult to train an agent in these circumstances. Diversely, if you have multiple agents used to gather data, possibly multiple human experts or a combination of human experts and real agents that are used to gather the data, and you want to train an offline reinforcement learning algorithm on this data, it is also, we know this has an impact on the performance, and there are some settings and some situations where we know this can either help or make it more difficult for the agents to learn. And then there are we know that using suboptimal agents might also impact the performance of the downstream offline reinforcement learning agent. And probably surprisingly, the usage of non-optimal agents is not necessarily bad, because as is hinted in the first point there on the top left corner, if you have a policy which is used to gather the data, which is very focused in the sense that it also always outputs the same action for the same in the same state, we don't have a very diverse set of examples to train our offline reinforcement learning algorithm, and it will be, or at least in some situations, it will be more difficult for this offline reinforcement learning algorithm to be able to learn what would happen if it did a thing other than the one that is being done in the batch of data, because it doesn't have much evidence about what actually happens. And lastly, and perhaps more importantly even than these problems that exist related to the sampling acquisition, there is, so most of this research, and as I'll show you during the demo, is based on the following framework. So you train a normal RL agent on a normal environment. Let's say, for this example, as it will be done in the demo, you train a DDBG agent on a particular environment, and you store the transitions in a buffer. Then you use your offline reinforcement learning agent to use this batch of data and no interaction with the environment, and you train it on this batch of data. So it hopefully learns how to behave properly in the environment, and then you have to test it. But the only way you have to test it here is by using the environment. But if we're trying to use offline reinforcement learning, especially in situations where we don't have this environment, and if we're relying on this environment to do the evaluation of the model, well, then we are here with a problem when trying to evaluate our model. So if I'm tackling a problem for which I don't have a simulator, and I'm trying to use my offline reinforcement learning agent trained on a batch of data, I can do it, but it is not very clear how can I then evaluate my model without using an environment. So this is an active topic of research where some interesting questions are starting to appear, and then going to the benchmarking part. So there are now some data sets, very recent data sets for offline reinforcement learning, but this is still in the early stages. And trying to go just a little bit further, delving a little bit further into this evaluation problem. There are some situations where there is research that points at ways to this evaluation. Namely, there is a pretty recent paper that kind of hints of a way of how to do this evaluation on special conditions of the MDP problem. And when we use offline reinforcement learning algorithms to train recommender systems, we usually are not after a model that necessarily has a good average return. So we kind of have other ways of evaluating our model. So in these particular situations, we kind of have a way of doing this, but in the general since we don't. So we don't have a way of doing this in the general setting, at least. And that's, as I told you, an active research topic. And particularly at Deloitte, we are interested in this problem mainly because it greatly contributes to the applicability of these things to real world problems. And we are actively trying to research this area and trying eventually to make some publications in this area. And we're making an effort in that direction. So here, the main takeaways for the talk, which I think I answered basically all these questions. And now I'll try to do a quick demo showing you how you can train your own offline reinforcement learning agent in a toy environment. So here's some references for some interesting papers. I think I covered, at least I touched in every one of them, but there is a lot more information there than the one I told you, I'm sure. So I don't know if anyone has, if there is a question, we can try to answer it. If not, I think, go to the demo and we'll do the questions later. So here I have a small notebook, which comes from basically the code base here comes mainly from a paper, which is the BCQ paper, which is on the references, and you also have the link to the GitHub on the files here. So if you want to see the original code, you can see it there. It is sitting on my GitHub, but I believe it will be added to the organization's GitHub too, so you can get it from there too. What I'll do, I'll try to show you how you can use it in the collab environment. You can run it on your PC, no problem with that. So the way you do it is you open the collab, you log in, you go here to GitHub, you paste the link to the repository, and you can open the notebook. So the notebook should run as it is right here. One thing you probably want to do is change this to use GPU so that it works a little bit faster. This is here as Markdown, but you have to, so this is just housekeeping stuff, just making sure the environment is the correct version, the GME has the correct version, and installing some things which are necessary just to show you the results down there. And getting the code from the repository, the remaining code from the repository. So nothing much here. So you can run this here. If you're using this on your own computer, well, the setup might be somehow different. So basically what I'm doing here is I'm importing PyTorch and other libraries, and what interests me most here, because we're talking about offline reinforcement learning, is the code base from the BCQ paper. So basically, what I'll show you here, and I'll try to get into the details in a couple minutes, is, well, I'll just load an agent that was trained offline, that is, it never saw the environment, and we'll try to see what how it behaves, just to show you that it actually works, and then we'll get a little bit into the details of the implementation, just to show you roughly how the implementation of what we talk during the talk can be done. Again, this code is almost exactly the one on the paper. So hopefully this will it worked. So as you can see, it kind of worked. So I don't know if you know this gym environment, but basically the idea here is that you have to land your moon lander between the two flags. And just for you to have a notion, if you never saw it before, I'll show you how untrained agents would do something. if the agent was untrained, something like this would happen, or some variation of this. So it is very difficult to land the moonlander at random. So this is just to show you that it works. So the process that is used in the paper and that you can reproduce by using this main.py file is that this is a three-step thing. So you first train an agent, which in this case is a DPG agent. You train it on the original environment just to gather the data. You gather the data and you store the data. Then you run this script again, and this script will generate the buffer from the trained agent. So you have a trained agent, you build the trained agent, you generate the buffer, you store the buffer. And then the third step is trying to train this BCQ agent on this batch of data without ever looking at the environment. So I didn't make any changes here. The only thing I changed here is just a way to save the model at the end, because in the original repository it's not been saved, so that I can show you this here. And I'll try to show you a little bit what's in the code. So this has an actor. This is basically a variation of an actor critic method. So you have an actor, you have a critic. The critic is pretty standard, but the actor has all those things that I told you about. He has a VIE that has to be trained. So I'll try to show you that. So let me try to show you. So this is the VIE. The way that the training goes is pretty standard. So you initialize your nets. This is, by the way, this is a PyTorch implementation. If you take the trouble, there are some TensorFlow implementations also available for the same paper. They are, I should warn you, a little bit slower than this one, but for small problems it might be okay to use them if you prefer TensorFlow. But so basically what I wanted to show you is that this VAE is used for is training with the reconstruction loss, as I told you. Then we use this KL divergence between the parameters of the encoder output by the encoder and the reconstruction loss, and we train it in this way. And then to train the augmenter net, which was the part that I didn't show you. You basically so you generate actions with this VAE, the decoder part, which is used using this function, which basically just uses the decode part to generate an action, and then outputs this action to the critic, and this is then used here as, I don't know if I can. This is what I would like to show you, because it's not on the pseudocode there. If we go on where is it? So it should be in the actor here. So basically, when we are acting, so in the forward pass to the network, we are generating the actions, but we are actually taking the perturbation network and multiplying it by this phi here, which basically is a very small number. Here it's 0.05. So this is the way in which we are constraining the actions to be very close to the actions generated by the behavioral cloning portion of the algorithm. And this of course makes the assumption that I told you about, that, well, actions that are just a little bit different from the original action should produce similar results. But here, in this particular paper, another assumption is made, which is that the agent is equally sensible across all actions, which you can arguably live with in most environments, because you can normalize these actions and kind of make them be in the same range. But it is an assumption that is here and is not talked in the pseudocode there. So if you want, this is the rest of the networks are pretty much just the feed-forward nets. The critic is pretty standard feed-forward net. The VAE I already told you about. The critic is pretty much the group of the behavioral cloning and the augmentation part. The training is pretty standard too. I guess it's pretty straightforward to implement this following the pseudocode apart from those small things I told you. But again, this implementation is in the GitHub for the paper, so you don't have to implement it just yourself. So, and the way you use it also is pretty straightforward. You initialize your environment, you initialize your network, and you load it. By the way, to be able to load it, you have to use my code and not the one on the paper, because the paper doesn't have a function to load and save, but it is pretty straightforward to implement it. And then you can run it on the environment for a couple of steps, and you can record the video and see how well it did. And that's basically it. So you can now try this on a different environment and see if it works. You can try to apply it to a real problem. So I think that's basically it. We have 1 hour now, so I think we're on time. Maybe.
Hey, José. Well, thank you so much. That presentation was awesome, and we have quite a few questions. We're gonna try to answer them all. So let's go one by one. I will put them in the screen so that everybody can see all the questions that were posed. Let's see if we can tackle them all. So the first one that was posed by José was, is the agent state also considered part of the environment state?
Well, usually there is no clear way to, it is usually somehow difficult to make the distinction of what goes into the state. But usually when we talk about state here, we're talking about the state of the environment, which may include the position or something about the agent itself. So I'd say yes, but I would say I can think of an example, but there might be situations where you don't want it to include in the state of the agent.
Okay. Now, this question also from José, is the constraining of policies a way of implementing a safety mechanism?
It might be, I think, if you're sure that the data that is in the batch is safe, because it might not be. You might have, so if you're trying to make the policy be similar to the behavioral policy, and the behavioral policy is doing something nasty, well, you'll end up doing something nasty probably by making this constraint too strong. But it can be used as a way, a safety mechanism, I would say, to try not to go a lot in very different directions than the one you see on the batch, I think. So I think, yeah.
Okay, all right. And the next one is, so BCQ is an action critic type of model?
Yeah, I think it is a modification on an actor critic model, in the sense that you clearly have an actor, you clearly have a critic there, and they kind of interact in their way. Albeit the actor is somehow more complex than you see in normal actor critic algorithms.
Okay, all right. And what is the difference between offline RL and off-policy RL?
So the idea, trying to make the distinction very clear here. So the idea of off-policy reinforcement learning is that the data you're using to fit your model is somehow different than the one that you would get when you use a policy that is greedy with respect to your value function. But still, the data that you use to fit your model and the data that your model would produce when used would be somehow similar. So they are similar. in offline reinforcement learning, the data might be completely different from the data that you'll see when you deploy your model, because you might even have the data being gathered by something or a human that is not a RL agent. So the agent will behave in different ways. So, and it will probably visit different states and do different actions. If you don't constrict it to be similar to the data it sees, it will potentially do very diverse things, and you will end up with an estimation error value, which is well, it's very big for completely offline settings. So it is unmanageable for to use this offline thing with no constraints at all.
Okay. And which RL algorithms don't follow the Markov property and also take in consideration previous states?
Well, I don't believe I'm fully qualified to answer that. I can't think of anyone that I know of which doesn't follow the Markovian property, but there are certainly models that are not based on the assumption that the current state has all the information needed for the compute the optimal action.
All right, and Olem asks, is this kind of RL the one used for trading stuff? What are current applications in the real world? Since you work in industry, what can you tell us about the real world view of reinforcement learning?
So I hope I'm not
besides.
So all these papers and there is some history of research in this area, but the two papers I presented to you are probably 1 year old or even less, I think. So this is a really recent area of study. I mean, a few years, at least with these kinds of models.
Mm-hmm.
So there isn't there aren't many use cases with real use cases using this stuff, because it is pretty recent.
Pretty recent. All right. So, and this is not exactly a. Sorry, were you going to say something, José?
Yeah, just a little remarks. But you see this applied on things like recommender systems. So you can frame your recommender system problem mostly as a reinforcement learning problem, and there are some, and there the off policiness is not that big of a problem, at least in some situations. So you have some claims that you can use these off policy methods in reinforcement learning without many of the problems that you have in other settings. So there might be some use cases there.
I see. And this is not exactly a question, but Vikram showed he really liked your presentation. He was saying that I'm working on a very similar problem in PhD. I'd love to get in touch to bounce some ideas. And then after he said, I'm using DeepRL for a control systems problem, a system with many degrees of freedom. So I want to constrain the exploration space to states that are close to the optimal policy and distribution. So this is not exactly a question, but just to lay it out to you, the speaker, that Vikram had an interest of bouncing some ideas off for his PhD research. And since here at the Meetup, we love connecting people, we pointed out.
Yeah, just a quick remark. There is also a distinction between what is usually called safe reinforcement learning and offline reinforcement learning. There are some connection between the two, and some of the methods, especially the uncertainty estimation part, is often used to try to constrict or focus the exploration to be sometimes safe. But the problems are somehow different in some situations. But there is a connection, I think.
I see. And finally, Gerardo asks, is there a way to make a policy robust against manipulation by adversaries? What do you think?
Well, I'm not sure.
Okay. All right, that's fair enough. I think that concludes our presentation. First thing I want to do is I want to thank José Thank you so much for sharing your time. The presentation was great. I feel like there was a lot of engagement, and the presentation was like so intuitive. It was really nice. We really, from the Deep Learning Sessions Meetup, we want to thank you so much for your presentation. It was great. Thank you so much, and hope to see you next time. All right.
Likewise. So thank you for the invitation, and I hope to see you next time.
All right. Thank you so much, José.
Thank you. Thank you.
Thank you. Now, before we wrap up, I just want to, in the name of Deep Learning Sessions Meetup, I want to thank everybody for coming. Thanks for your questions. Thanks for your engagement. This concludes the 2 talk series that we had from Deloitte about reinforcement learning. In the future, we're planning some Auto-ML talks and some Intro to Deep Learning talks, and we'll sure to let you guys know at the Meetup group. Don't forget to fulfill the forms and give us your feedback. We really want to improve, so please let us know what we did wrong, what we did well, so that we know how to provide you with the best event and the best presentations possible. Thank you so much for everything that you guys did. Don't forget that the GitHub will be available. The GitHub will be available after this presentation, a link to the slides and to the GitHub. And we have a form for you to apply if you're in industry or you're an academic and you want to present with us. Just let us know. We have a form where you can apply, and we'll get in contact and we'll start thinking about how you can present. Okay? So thank you so much, and see you next time.